There is a common pattern that shows up in most concurrent systems, which is that many threads read and write to a shared data. Considering both type of access the same way is inefficient, and there is a way to make our system more concurrent and hence more efficient. Today, we are going to discuss all about this classic process synchronization problem called the readers-writers problem. Let's go through it. In the previous videos from this playlist, we saw that when threads share data, things can go wrong. Mutex and semaphore are the tools we use to fix that. In the last video, we discussed about one process synchronization problem, that is producer-consumer, which deals with coordinating multiple producer and consumer threads that add and remove data from a fixed shared buffer. Today, we will look at another classic process synchronization problem, that is the readers-writers problem. What happens when some threads only read shared data and others write to it? And how do we coordinate them to achieve maximum concurrency? Let's understand the problem first. You have a shared data store, a database table, a cache, a config object, etc. Multiple readers and multiple writers access it concurrently. But readers and writers behave very differently. Readers only read, they never modify the data. Multiple readers can be active at the same time without any issue. They don't interfere with each other. Blocking them when no writer is active is unnecessarily conservative and kills concurrency. On the other hand, writers modify the data. A writer needs exclusive access. No other thread, reader or writer can be active while it's writing. Our goal is to maximize read concurrency while guaranteeing write exclusivity. Here's the key insight that drives the entire solution. Reader plus reader means no conflict. Two threads reading the same data simultaneously is perfectly safe. Neither is modifying anything. You can allow as many simultaneous readers as you want. A writer plus anyone leads to conflict always. A writer modifies data. If any other thread is active at the same time, you either corrupt the data or a reader sees an inconsistent snapshot. Look at the conflict matrix. Reader versus reader, safe. Reader versus writer, conflict. Writer versus writer, conflict. We can solve this problem with a single mutex, but it would kill the concurrency as it will provide exclusive access to the critical section to both readers and writers. But as we understood, only writers need exclusive access and multiple readers can safely run in parallel. That's the problem we are trying to solve. Three things can go wrong without proper synchronization. First, two writers running simultaneously. Both modify the same data at the same time. One overwrites the other changes. This leads to classic race condition. Data is silently corrupted. Second, a writer running while readers are active. A reader accesses the data mid-modification. Some fields are updated, others are not. The reader gets an internally inconsistent snapshot. This is worse than a crash. The program continues with bad data and you may not notice for a long time. Third, writer starvation. Readers keep arriving in a continuous stream. The writer is waiting for exclusive access, but new readers always jump ahead. The writer waits indefinitely. The system is doing work, but the writer never makes progress. This is a liveness failure, which is equally important to correctness failure in production systems. The solution uses one shared integer and two semaphores. Read count starting at 0. This is a plain integer, not a semaphore. It tracks the number of active readers. Mutex, initialized to 1, this protects read count. When multiple readers arrive simultaneously, they all try to increment read count. Without a mutex protecting it, two readers could both read the same stale value and both write back a race condition on the counter itself. Read-write lock, initialized to 1, this is the actual write lock. The first reader to arrive acquires it, blocking all the writers from entering. The last reader to leave releases it, letting a waiting writer in. Writers acquire it directly for full exclusivity. Let's look at the full pseudocode. Initialization, mutex starts at 1, RW lock starts at 1, read count starts at 0. Reader's logic is, first wait on mutex to lock read count, increment read count. If this is the first reader, read count equals 1, wait on RW lock to block writers. Signal mutex to release read count. Now read the data. When done, wait on mutex again, decrement read count. This is the last reader. Then signal RW lock to let a waiting writer in, and then signal mutex. Writer logic is much simpler. Wait on RW lock to get exclusive access, write the data, signal RW lock to release the lock. Notice the asymmetry. The writer is just two meaningful lines. All the complexity lives at the reader end, specifically in the first reader and the last reader. The first reader acts as a gatekeeper that locks writers out. The last reader is the one who opens the gate again. Now, let's understand the priority trade-off between readers and writers. Reader priority. New readers are always admitted even if a writer is waiting. This leads to maximum read concurrency. Readers never block unnecessarily, but writers can starve if readers keep arriving. This is good for read-heavy systems where slight staleness is acceptable, like DNS resolvers, read-heavy caches. Next, writer priority. Once a writer is waiting, no new readers are admitted. Writers get in as soon as current readers finish. No writers starvation, but reader may wait longer on write-heavy systems. Good when stale data is costly, like stock tickers, real-time dashboards, etc. Next is fair or hybrid approach. This is where we alternate between reader and writer groups using a queue. Neither side starves. This is slightly more complex and has a slightly lower peak throughput, but this is what most production systems use and what major language libraries default to. Let's see some real-world examples where this problem pattern is seen. Databases, select queries are readers, insert, update, delete are writers. Most databases uses MVCC, which is multi-version concurrency control, which is a more advanced version of this pattern. CDN cache. Cache read happens millions of times per second. Cache invalidation, the writer is rare. You want reads to proceed without any blocking. Config system. Services read config values constantly. Config updates are rare. You don't want a config read to block other reads. DNS resolver. DNS lookups dominate. DNS record updates from TTL expiry or manual changes are rare. You don't want a DNS lookup to block other reads. That's it for today's video. I hope you now understand all about the readers-writers problem. If yes, then please do like this video and comment down if you have any questions or if you want me to cover any other topic. Subscribe for more such content. See you in the next one.